Welcome to the last lecture of the course. So today's the day of celebration. This is the last lecture that we're going to have together on video. And we're going to learn how to solve the two-dimensional Laplace equation. As we discussed when we introduced all these equations, the Laplace equation is very important. It's important in gravity, it's important in electromagnetism. It is the equation that the potential satisfies in a region that is devoid, that there's no mass, if it's the gravitational potential, or no charge if it is the electrostatic potential. If you wanted to figure out what are the electromagnetic what is the coverage of the router that you have at home, depending on the rooms and the walls and so on, you have to solve a way more sophisticated, I have to say, version of this, but still something that the fundamental principles of this are here, okay? Of what you have to solve in this equation. Now, solving it in 3D, it's more complicated than solving in 2D, arguably much more complicated, but this is the first step that you need in order to solve it in 3D. Okay, so in this course, we'll solve it in 2D. Now, in 2D, imagine something like that. You have a capacitor that is flat, and then you have in a two-dimensional capacitor, something really thin, and you have wires, right? And in these wires, you set a potential profile, like that is a function of y. This is the y-axis. This is the x-axis, and every border of it is got a potential, a configuration of potential. You put it there. You have to set the charges in a particular way to create that potential. And then you ask, what is the potential inside when there's nothing? There will be some potential. What is it? Because there are charges here generating these potentials and so on outside. We can tell that this is kind of similar to the wave equation, right? Only that the signature of the two terms is the same. It's not opposite. Now, there's another difference, right? There's no time. They're both spatial variables. They're related. That difference is related, of course, but they're both spatial variables. And as such, we have no initial conditions. They're all boundary conditions. We have 4 boundary conditions. Now, those boundary conditions are literally the conditions on the boundary of this flat capacitor that you have here. And the techniques that we're going to learn, what is special, I mean, it's basically more of the same, but what is special about this, solving this equation, is that we're going to learn how to apply boundary conditions when they're given at points that are slightly tricky, as we will see. All right, so let's begin. What do we do in this case? You can tell that the 4 conditions, I mean, oftentimes we're used to saying, right, the conditions, we have some boundary conditions that are homogeneous or non-homogeneous, but with some value and so on. Well, here, they're definitely non-homogeneous, all of them. So, you see, I mean, in this, so check, when x is equal to 0, so that x is equal to 0 is the y-axis, right? And for all y's, there's g1 of y's. You see on the y-axis is on this wall, we have this function g1 of y. When x is equal to L, so here the length of this is L, is the length of the side of that square. It's L everywhere, right? So this point is the point LL. This point is the point XL0, 0y. This is the origin, 0, 0. And this is the point 0, 0x and L height. All right? Now you see that the conditions that we imposed, for example, this one, the green, I color-coded them, because we're going to use that color code later, and I will specify for colorblind people. It's convenient and organized to do it color-coded, but I will certainly specify try to make it clear where we go. So we have a condition on the left wall, a condition on the right wall, a condition on the lower wall, and a condition on the upper wall. Now, remember, solving this with non-homogeneity is extremely complicated, but what we can use is the trick that is a linear equation. So if I get a solution to the equation, then sum of solutions to the equation is a solution to the equation. And what I'm going to do is I'm going to decompose this into 4 different problems that you have to solve, 4 different problems, and these 4 different problems will have only one inhomogeneity. And we will treat that inhomogeneity a little bit like we treated an initial condition. Okay, so let's see in the previous examples. So let's see how we do it. First, let me write decompose in 4 problems. So I'm going to do problem 1. Problem 1, I'm going to call it the problem for the wall. I'm going to call it the down problem. And the down problem is partial mu of some function that I call u down, arrow going down, with respect to a square, equals second derivative of u, sorry about that, second derivative of u down with respect to y twice. And for this problem, I'm going to impose that the non-homogeneity, I'm going to impose the one in the down wall, the one that is in green here. U of x0 is f1. So I'm going to say that u down of x0 is f1 of x. And all the others, well, all the others, u down of all the others, which is xl, equals u down of 0y equals u down of ly equals 0. That's problem number 1. The down problem. I put the inhomogeneity in the down one, and all the others are homogeneous. Another problem. This one I'm going to call it the up problem. So the up problem, square x squared equals second derivative u up y squared. All right. And now, what am I going to do here? So it's the same equation, as you can tell. They're all solutions to the Laplace equation. But I'm going to impose on this one that the burden of this one is going to carry the burden of satisfying the inhomogeneous boundary condition on the up wall. So this would be that u up. The up wall is the one in purple here. So uxl equals f2. So u up xl equals f2 of x. Wonderful. And for all the others, u up of x0 equals u up of 0y equals u up of ly equals 0. So this one is the problem with the inhomogeneity only on the up wall. You may imagine what comes next. We're going to have the third problem that is I'm going to call it the right problem. U right partial x squared equals partial square u right y squared. And then this one is going to carry the burden of the condition on the right wall, which is the blue condition here. U ly equals g to y. U right of ly equals g to y, and all the others are going to be 0. So u right of, I'll put myself here, of x0 equals u right of xl equals u right of 0y equals 0. So it's homogeneous in all of them except for the right wall. All right. And finally, the fourth problem is going to be the left problem, and the left problem is with an arrow to the left, x squared equals second derivative of u left with respect to y. And this one we're going to load the burden of satisfying the left wall boundary condition, the red one on this one. So we impose that u left of 0y, try to write this better, 0y is equal to g1 of y, and all the others, u left arrow of x0 equals u left arrow of xl equals u left arrow of ly equals 0. So those are 4 problems that are solved in a very similar way, in fact in an identical way. Only you see why these problems are cool in themselves. So maybe you're still wondering how solving this gives me the total solution to the full one. Well, we will address that right now, but first, these ones are easy because even though they're all boundary conditions, I can treat the homogeneous the same way I always treated the boundary conditions in the past, kind of. We will see exactly how that works. And one of them is going to be like the initial condition. In a way, this is going to be the last one that we impose. Okay, we're going to impose first these ones that are simpler, and then the last one here. Now, the question is, if I decompose it in 4 problems, then I'm going to claim that the total solution, u of xy, has to be equal to the sum of u down of xy plus u up of xy plus u right of xy plus u left of xy. Let me color code it. And that I associated a color u down is associated with having the homogeneity down, purple up, blue right, and red left. Now, if you look at what we have here, if the question that we ask, well, is this a solution to this equation? You need to change two things, right? We need u to be one, solution to the Laplace equation, to one, and then two, satisfy simultaneously all boundary conditions. That's what we need from this u. That's what the problem asks you. Find u, that is a solution of this equation satisfying these boundary conditions. All right, so let's check if we have it. Is one a solution to one if I write like that? Well, yes, because it's the sum of four solutions of this equation. So certainly it is a solution of the Laplace equation, indeed. Okay, wonderful. Does it satisfy simultaneously? So this is a tick. Does it satisfy simultaneously all boundary conditions? Well, let's check. First, let's check the condition, that one. U 0, y. Okay, that's equal. What is u down at 0, y? U down at 0, y is 0. All right, plus. What is u up at 0, y? U up at 0, y is 0. What is u right at 0, y? U right at 0, y is 0. And what is u left at 0, y? Or g1. So, oops, of x. Of y, sorry. g1 of y. All right, so what is the final result here? Well, that u0y is equal to g1 of y. Nice, it definitely satisfies this one. Wonderful. Let's see. We keep going. What about u-ly? Okay, u-ly. U down at ly is 0. U up at ly is 0. U right at ly is, g2 of y. g2 of y. And u left at ly is 0. So we get g2y. Oh, nice. The sum of the four satisfies this equation. All right, let's do the two others because completeness, right? Although you see how it's where we're going with this. U of x0, okay, u down of x0 is f1 of x. Then u up of x0 is 0. U right of x0 is 0. U left of x0 is 0. So this thing is f1 of x. And that means that we satisfy this one. And finally, u of xl. Okay, u down of xl is 0. U up of xl is f2 of x. U right of xl is 0. And u left of xl is also 0. So what we get is f2 of x. So indeed, we satisfy all four boundary conditions. So yeah, we got the solution to our problem. Solving these four individual problems that are easier to solve, we can solve the full problem. That is, the solution to the full problem is the sum to the solutions to the four problems in which we put the burden of the inhomogeneity only in one of the problems, in one of the boundary conditions, in one of the borders. All right, so now if we were to do the whole thing, we would take 2 hours probably, and we will solve the four problems, all right? Because they're all the same, basically, they're very, very similar. We're gonna solve problem 1, so you see the kind of issues that you will find when you solve it. And I'm gonna ask you to solve problem 2, 3, and 4 and give the final solution. Shall we? They're very, very similar. Okay, so let's do that. Let's solve problem 1. All right, so the problem of the 2D Laplace equation, in this case, the problem 1, subproblem 1 is the same as well. I have 0 in all the walls, 0 potential, and I have some potential profile on the lower wall. So let's see what the potential is inside. All right, so the first thing that we do is same as usual. We separate variables. We ask math, will the solution be a product of a function of only x times a function of only y? And then if we introduce it in the equation, we get the same as before. Introduced in the equation, we get that the equation becomes x dot dot of x, y of y, plus x of x, y dot dot of y equals 0. All right. So then what we find is that on one side we have x dot dot, put in all the same variable on one side of the equation and the other variable on the other side of the equation. X of x equal y dot dot of y divided by y of y. Okay, and then we come to the realization. You see, one has different sign than the other. Okay, so we come to the realization that if this thing is only a function of x and this is only a function of y, and this has to be equal for all values of x and y, the only possibility is that this is not really a function of x, because this is not either, and that this is not really a function of y, because this is not either. So this has to be a constant that I call lambda, the separation constant, which is the eigenvalues of the problem. All right, so that gives me two equations, and one of them is x dot dot of x minus lambda of x equals 0. So the characteristic equation for that one is m squared minus lambda equals 0. All right. So we see in this case that m is equal to plus minus square root of lambda. Okay. And on the other hand, we have u dot dot of y plus lambda. See, the signature is different. Plus lambda y of y equals 0. Now you see from this other two equations, the first one is this equals lambda, second one is this equals lambda. Okay? And the characteristic equation here, let's call it L, it's L squared plus lambda equals 0. So L is equal to plus minus root of minus lambda in this case. All right, so again, these two equations, remember this one came from x over x equals lambda, and this one y over y equals minus lambda, first and the second. And both are second order linear ODEs, constant coefficients. We've solved 1,000 before, and depending on the value of lambda, if the sign of lambda, we'll have different kinds of solutions. If lambda is positive, we will have, if you remember, well, depending, because the cases are mixed actually, but for lambda positive, lambda 0, lambda negative, we can have exponentials or sinches and coshes, trigonometric, causes and sines, or polynomials. Okay? So let's see what we have in this case. Case 1, lambda is equal 0. So in those cases, we have both m equals 0 double and L equals 0 double. All right, so in this case, we get that x of x is equal to bx plus a, and y of y would be equal, let's say cd, dx plus c, dy, sorry, plus c, for example. All right, wonderful. So the solution will be the product of the two, and again, we don't need the four constants, but we put them there for convenience until the end. Because, you know, they're a product, so one of the constants I can absorb into other two, all right? But let's keep it like that for now, and at the end we'll discuss if we have to do something like that. All right, that would be case 1. Let's see what case 2 is. Case 2 is lambda is larger than 0. And in this case, let me call lambda omega squared. Let's say lambda, we're going to call it omega squared, okay, as before. In this case, we have m, it's equal to plus minus the square root of lambda, which is omega, so it's plus minus omega. But interesting enough, L would be plus minus I omega. You see, it's minus the square root of minus omega. Omega being positive of omega squared, right? Omega squared is positive, minus omega squared is negative, so we get an I. So you see the cases that we saw before in this one mix. So that is interesting in this case. It's a difference with before. Okay, so what we get in this case is that x of x is exponentials or sinches. We're going to use sinches and coshes to get you used to that also because it's simpler in general terms. So let's write both. we have some constant a, let's call tilde the one that is not the sinus, a tilde e to the omega x plus b tilde e to the minus omega x, or alternatively a times the cosh of omega x plus b the sinh of omega x. What about the y's? Well, now the y's are different. The y's, you have, this was a case of two real roots, and here we have the case of a pair of complex conjugate roots with no real parts, so no exponential multiplier. So this one, as you remember, it's c cosine of omega y plus the sine omega y. All right, that's case 2. And finally, case 3, lambda is negative, so we call lambda minus omega squared, and we get that m is equal to plus minus I omega, right? Square root of minus omega squared, but L in this case is just plus minus omega, mx. So in this case, we get that x of x is equal to a cosine omega x plus b sine omega x, and y of y it's equal, let's write directly the coshes. I mean, we know it could go out right both. C tilde e omega y plus d tilde e minus omega y, or alternatively c cosh omega y plus d sinh omega y. Usually cosh and sinh much easier to apply boundary conditions like that, that are homogeneous like that. Alright, so we have the 3 cases. Let's summarize them and put them up and solve our specific problem, shall we? Alright, we summarize the cases up here. And now we're going to do what we know, what we do. We'll apply, let's call this the NHBC, the non-homogeneous boundary condition, and this one the HBCs. This video is not sponsored by HBC. Alright, so what we do first is we want to impose first the homogeneous boundary conditions, and in particular the ones that are on x, on the same variable first. In this case x, but in other subproblems it will be y first. The ones that are on the same variable, okay? X equals 0, x equals 0. So we impose those ones first. So impose the HBCs, the following two. U down of 0y equals 0, and U down of Ly equals 0. Those are the 2 first conditions that we need to impose. All right? And let's check case 1. Case 1. So in case 1, well, that for all cases, this means that x of 0 is equal to 0, capital X, and this means that x of L is equal to 0. All right, because YL is true for all y's, and you can divide by the 2, and you got it. All right, so if we impose that, we get from case 1 that b times 0 plus a equals 0, and that means that a is equal to 0. From this one, we get bl plus a equals 0, and that means, because I use a equal to 0, that bl is equal to 0. 2 possibilities. Either L is equal to 0, which is inconsistent because we have some finite extension here, or that means that b is equal to 0, in which case it is a solution, but it's the trivial solution. Trivial solution, all right, which is u down equals 0, and this trivial solution, unless f1 is exactly 0, is incompatible with the conditions where f(x of 1) is different from 0, when you have something in there. All right, wonderful. So case 1 is discarded. Let's check case 2. For case 2, we check the same HBCs, the homogeneous boundary conditions on x. And we're going to use the cosh and sinh expressions because are much simpler. So a cosh of 0 plus b sinh of 0 equals 0. That's easy. The sinh of 0 is 0 and the cosh of 0 is 1. So that means that a is equal to 0. How nice. All right, wonderful. So the second one tell me a cosh of omega L, right, plus b sinh of omega L equals 0. But I know, because a is equal to 0, that what this is really telling me is that b sinh of omega L is equal to 0, several possibilities. So either b is equal to 0, which would give me the trivial solution, the same that incompatible with a boundary condition f1x different from 0. Okay? If it were 0, then that would be the solution. But if it's not, it's incompatible with it, because it's 0 always. So that is discarded. And the other option is that the sinh of omega L equals 0. But that means that, because the sinh only has one 0, that omega L is equal to 0. And that means that either L is equal to 0, are inconsistent, we have a finite size here, or that omega is equal to 0, are inconsistent, because in case 2, remember that lambda is larger than 0, so omega is larger than 0, omega squared is larger than 0, so it cannot be 0, omega, alright? So this gives no solutions as well. Alright, so if there are any solutions, they will be in case 3. Let's see it. Alright, on case 3, we get that that would be a cosine of 0 plus b sine of 0 equals 0. Wonderful. This is 1, this is 0, so this is telling me that a is equal to 0. And the second one tells me that a cosine of omega L plus b sine of omega L equals 0. But I know that a is equal to 0. Therefore, that is telling me that b sine omega L is equal to 0. Several possibilities. Now we have on the one hand that b is equal to 0, but that is the trivial solution with a equals 0 and b equals 0, trivial solution that we already discarded because it's incompatible with f1 different from 0. And if not, we get that the sine of omega L is equal to 0. And now we get an infinite number of solutions and gives actually the value for the eigenvalues of the problem, the omegas. So that would be true for omega L equals to n pi. And that happens for many omegas. Let's call it omega sub n. Omega sub n equals n pi over L. All those give me solutions. Wonderful. So all those give me solutions. Now I know the value of omega n. So I know what the x's would be like. So case 3 gives me solutions of the form x of x is equal to x sub n bn sine of omega n x, which is n pi over Lx. I have infinitely many of those. Now what about the y's? Well, in this case the y's would be of the form of this form is case 3, so coshes and sinches. So that would be c cosh of n pi over Ly plus d sinh n pi over Ly of this form, okay? I don't know how many of those we will get, but it would be, now of course there would be sub n and sub n and sub n, okay? But I don't know if I would have all of them or not. We'll see. We need to keep imposing boundary conditions. So the next step is impose the HBC on Y, which is this one here. Now we can call this one the lone HBC. For other cases, the one that is alone. This is a condition. This is a condition on x equals 0 and n equals L. So that's the first one you apply. The ones that come in pairs. Okay, conditions on x first, and then you apply the condition on Y. Here's something that in past courses people got confused with. They say, why is this a condition on x? This is a condition on y, because there's y's in here. No, it's no. It's a condition on x in the sense that we say that when x is equal to 0, this is 0, and when x is equal to L, this is 0. So there are two conditions on x here. In other problems, you would have two conditions on y. If you're looking at a problem that the homogeneity is here and there's a 0, you get the two homogeneous conditions paired on y. All right? So first, solve the pair of conditions, and then you solve the lone condition, then it's still homogeneous. All right, so if we do that, we need to impose that the condition here was that u down of xl is 0. And that means that y of L is equal to 0. All right, so to impose this one, we're gonna do a trick on the y. This is the only difficult part, I guess, different part of solving this, because now, you see, usually when you impose conditions like that, the second one on L is accompanied by one on 0 that cancels one of them and makes everything super easy. You see, in all these cases, you're getting one of the constants equal to 0. But now you cannot do that because you don't have a condition on 0. So we're gonna do a little trick to impose the condition here in a nice way. Let's go back and see what y of y was in this case. Y of y was c tilde exponential of omega y plus d tilde exponential of minus omega y, right? But I can do the following. I can write this, if I want, as follows. I can say, let's see, c tilde, and I'm gonna add here the exponential of omega L, if I want, but I multiply by that and I divide by that again. So it's omega y minus L. You see? E to the omega minus L cancels the omega L here. I did nothing. You see, I added this and I divided by the same. I did nothing there. Plus d tilde e to the minus omega L, and then I get d tilde, e to the minus omega y minus L. See what I did? I did nothing, because this thing, if I expand it, is e omega L, e omega y, e minus omega L, and this cancels that. So I did nothing really. It's the same as on the left. But what I can do though, which is really nice, is, oh, this is an arbitrary constant, and this thing is a freaking constant, and this is an arbitrary constant. I can reabsorb and define new constants, c tilde tilde and d tilde tilde, for which I can write that this is c tilde e to the omega y minus L plus d tilde e to the omega minus omega y minus L. Oh, sorry, with double tilde. You see? And one more step, because I know these are combinations of exponentials, arbitrary constant. I can define new c and d, in which these are coches and sinh. C cosh of omega times y minus L plus d sinh of omega y minus L. Alright? So this is the little trick. The solution, the general solution in this case, can be written as C. So I'm gonna put this here because I'm gonna use this one for here, right? Right, so in this case I can take, with a loss of generality, because these are arbitrary constants, and my solutions are like that or like that. This kind of cautious adding, subtracting an L to the variable, because there's just redefining, you see, the constants that are arbitrary to begin with, and we're gonna determine after we impose the conditions. All right, please check this carefully if you need to, and if you have questions, please do ask in the review session, because this is the only difficulty of solving this problem. All right, let me erase the whole thing, and we can solve our problem, but notice that, of course, if we take this solution, we need to use, because the C's and D constants are with this solution, and we determine the C's and D's for this solution, we need to update and write this solution consistently with the value of the constant we found. Because, of course, we found that we're going to find statements about the Cn's and the Dn's for this form, not for the form that we wrote before, okay? So we redefine the constants with the new equation, with the new form that we have for the equation after translating the function, okay? It's actually pretty easy. It's the translational invariance of the problem. You can translate the problem and nothing happens. Anyway, so let's impose these boundary conditions now. So if we impose the boundary condition on y, we get that Cn cosh of y minus L is 0, so cosh of 0 plus dn sinh of 0 equals 0, and we know the sinh of 0 is 0 and the cos of 0 is 1, and that is telling me that all the Cn's are 0. So we only have sinh terms, not cosh terms. And singes of this displacement, okay? So this means that because of that, yn of y is just dn sinh of n pi over L y minus L. Wonderful. So now we need to construct all the family of all solutions, which is the product of these two, and then find the general solution as a sum of all possible solutions, and then find the coefficients via the Fourier series tricks that we already know. Let's do it. The u of xy, un, each of those solutions that are here, are the product of the xn of x with the corresponding yn of n with the same value of omega n, of course. And what we get, so now you notice that we have a constant bn multiplied by a constant bn. We can unify them and really find yet another arbitrary constant. Let's call that one, what do we call it? Bn. We reabsorb everything in terms of the bn, all right? So we get that this is bn. If you want to redefine bn, you call this one tilde and this one without tilde, but it's the same, it's just an arbitrary constant, okay? So we reabsorb the bn into the bn constant, because it's an arbitrary constant, and we get this is the sine of n pi divided by L x times the sinh of n pi L y minus L. All right, so these are each of the solutions. So if we want to write the most general solution that satisfies all the HBCs, most general solution to the Laplace equation satisfying all these HBCs would be of the form u of xy equals sum over n of bn sine n pi over Lx sinh n pi over L y minus L. There we go. Now we have to determine the coefficients bn, which are the only unknowns here, the arbitrary constants that are multiplying this, and we do that by impose the NHBC. And that tells me that u down x comma 0 is equal to f1 of x. All right, so let's write here u. This is of course u down, and these UMs are corresponding to the down problem that we have here all the time. So what we get, we write u down of x0 substituting y by 0. If we substitute y by 0, we get the following. Sum n equals 1 to infinity bn sine of n pi over L x. Actually, I'm going to write first the constant factor that we get there. That would be the sinh of minus n pi over L times L, multiplying the sine of n pi over Lx. We can simplify this quite a bit because the L's cancel and the sine I can take out of the whole thing, like that. And then this is equal to f1 of x. All right, so now we know that this is a sine Fourier series. So I know that whatever multiplies the sine, let me call this guy, this whole thing that multiplies the sine, let's call this thing small bn, all right? So small bn, if I call this small bn, let me just write it here. I define small bn as minus bn sinh of n pi, then I know that this condition is telling me, the condition is telling me that the sum n equals 1 to infinity of bn sine n pi over Lx is equal to f1 of x. And now in this form, I know for a fact, this is a parenthesis, I know for a fact that the small bn's are the coefficients of the sine Fourier series of f1 of x. So what is the sine Fourier series of x1 of x? Well, it's the Fourier series of the odd extension of f1 in the interval 0 to L. We extended to minus L to L with the odd extension, okay? So we know that the small bn's are, and let's do it complete once more. So the period would be 2L, right? So we have 2 over the period because it's the odd extension. The period is go from minus L to L, 2 over 2L, integral from minus L to L of the odd extension of f1 of x. So let's say f of x is the odd extension of f1 of x, all right, times the sine of n pi Lx. All right, the 2's cancel, but this is again odd because it's an odd extension, and this is odd because it's a sine. So we get twice. So again, we get 2 over L, the integral from 0 to L dx. Now small f, so f1 of x, right? Because from 0 to L, that's exactly what the function is. Sine of n pi Lx. All right, and those are the bn's. All right, but I don't want the small bn's, I want the big bn's. So I need to go here and find bn, it's equal to minus bn divided by the sinh of n pi. All right. So finally, the result that we arrived to, let me erase this. The constant bn would be 2L. Let's say if you want minus 2, minus 2 over L times the sinh of n pi times the integral from 0 to L of dx f1 of x sine of n pi divided by Lx. Okay, those are the coefficients Bn. And that gives me the full solution because the full solution is substitute this into here. Okay? And that will be the full solution to the problem. I don't think I would have to do it, right? I mean, it's just rewrite when you see at the end, write this thing here with the minus sign in it, and the sign and the constant in front, and compute from the f1 of x that you have, compute the Fourier coefficients, as we did in the problems for Fourier coefficients. If this is particularly simple, you should be able to determine the Fourier coefficients by inspection, same as before in previous problems. But that's it, that's the solution. That would be the solution to subproblem 1. Now you have to repeat this 4 more times. And again, the process is the following. First, impose, so write the problem, right? And then check all the cases, right? And impose, to check all the cases, to check which ones are going to give you solutions. You need to impose first the paired homogeneous boundary conditions, the one that are on the same variable. If it's one of the cases, this one or this one, it would be the conditions on x. If it's this one or this one, it would be the conditions on y. Then, after that, you impose the lone condition, the condition that is homogeneous but a loner, that doesn't have 2 for the same variable. And then finally, to determine the constants that we have, you need to use Fourier series techniques, imposing the non-homogeneous boundary condition. Right. One thing is that when the lone condition is on L, which happens in 2 of the cases, happens on these cases, well, in all the cases that this one or these ones are 0. So it happens when this case is non-homogeneous and when this case is non-homogeneous. When you have that, then it's much better to use the trick that I use to write the solution in terms of the translated solution. You can always translate the solution by L, and the result doesn't change, as I proved to you, because you can reabsorb the e to the omega L as constants, in the arbitrary constants. All right, I hope that this was clear enough. If not, please do come to the review sessions and ask me questions. And well, it's been a pleasure. It's been really challenging to record these lectures for me. I hope that I was able to transmit you some of the knowledge. If not, my apologies. It is the first time that I do something like that. It is extremely challenging to put these videos together. Trust me, the amount of hours that I put on this is more than the preparation that I do when it's in class. And I don't have the feedback of seeing the people. And I realize how much I rely on seeing how people react and ask questions in order to control my pace and control the rhythm at which I go, etc. So please bear with me. We will try to make the best of this course in terms of both of us, you and me, in terms of really learning stuff. And I really want you to learn the math. It's more important that you learn the math than focusing on grades. It's easy for me to say, of course, you're the ones getting the grades. But honestly, math is to learn. It is part of your toolbox that allows you to solve problems in the future. So, also something enjoyable. I hope that the connections with physics and with engineering that we saw also like kind of gave you some motivation to learn more of this. And again, I'm always happy and available to talk about any of these topics. Please contact me. If you don't want just in the review session, we could have one-on-one conversations in office hours as well. And well, that's it. We'll be seeing each other in the live sessions, and let's see how that goes. It's been a pleasure. See you soon.